Hi everyone. So today I'm going to talk about missing data, and for this talk I'm going to use some of the references, but the primary reference is this particular paper from BMJ from 2009 from Stern, Multiple Imputation for Missing Data in Epidemiological and Clinical Research, Potential and Pitfalls. So here is the content of what I'm going to present. First I'm going to talk about what are the impacts of missing data. Then I will talk about some of the types of missingness. Then I will talk about how people address missing data problem in their data. There are many ad hoc approaches and there are some principled approaches, and I'm going to talk about them. And later, after we are done with our explanation of how to address missing data problem, we will tackle some of the special cases of variable selection, what to do when the outcome is missing, and how this type of analysis can be done using the complex survey data. So in terms of clinical and epidemiological research, you will see that it is very common problem in clinical data because data can always go missing. Some data cannot be collected, cannot be measured, but the problem is that many of these clinical researchers are not equipped well to deal with missing data problem, and reviewers, especially the methodological reviewers, push for doing a proper missing data analysis, and as a result you will see in many of the literature or papers they do not even mention the problem of missing data, as if there was no missing data problem. And when the reviewer pushes even more, then maybe they do some suboptimal analysis, some ad hoc approaches. So this is a common problem for the not only the medical analysis but also in many other research areas. Couple of days ago we have done a literature review on a particular disease area, and even in that review we have found that many of the people do not even talk about missing data as if there was no problem. But in reality, whenever we are dealing with real data set, missing data can be a real challenge. Alright, so what are the consequences of missingness, having missing data? So obvious consequence is that if the data is missing in a way that systematically omits certain part of the data set, then your result can be biased. When you simply delete some of the subjects who have some missing information, or they are not comfortable to disclose all of their information, then you are also reducing the sample size, and that will give you some incorrect standard error or precision. And of course, when you are deleting patients, you are subject to losing power in your study. So in here I'm going to talk about some of the types of missingness. The first type of missingness is known as missing completely at random, and by random I truly mean random. Say for example, your data was collected, but someone who was typing your data, they forgot to insert your data, or maybe your data was in a piece of paper and they lost that piece of paper, and that has nothing to do with you, your information, or anything. It happened at random. So if that is the case, then we would label that problem as missing completely at random. And to be missing completely at random, the basic characteristic we are looking for is that the missing value versus the observed value, they do not have any systematic difference. It is just missing because of a random problem that occurred during the data collection or processing stage. And if that was true, that there are no systematic difference between the missing values and observed values, then we can simply do a complete case analysis. But even in that case, we would have this problem that our power will be reduced because we are deleting patients who have some incomplete information. And also, even though you will see many people are using this complete case analysis under the assumption of missing completely at random or MCAR, it is rarely the case. Usually there is a reason why some subjects are providing partial information. The second type of missingness can be missing at random, where missingness can be explained by the observed variables or measurements. That means that if we simply try to check the values or the persons that have missing values for a covariate versus the observed values from some other subjects, then usually it is possible to figure out whether that missingness or the people who respond less have a particular reason or not. Say, for example, if a subject has high income, often they do not want to report their income. Or if a subject has very low income, often they do not also want to report their income. So in that case, if you simply try to check whether the person's income level, often this is associated with some other factors such as socio-demographic characteristics, education level, and all of the other things. And if you try to check the bivariate tables, you can usually find out there might be a relationship between those that are not providing their income. They are from certain education groups, certain socio-demographic groups, and one way to solve that problem would be to borrow some information from those other variables that are indicative or predictive of whether a person is giving their income level information or not, and we can simply use those other variables such as the education variable and the socio-demographic status, and using those variables we can try to impute the missing income information. And also the scenario that I just described, that even though you have missing income problem, but you do have some other variables that are predictive of income, and using those information we are talking about imputing the missing observations. And this type of situation would be known as missing at random, where we are essentially utilizing the relationship of other variables with that missing information to impute those variables values. And in this type of scenario, if we try to do a complete case analysis, that would not be unbiased, in the sense that we are only including subjects who are not shy about reporting their income, and that says something about the missingness pattern. So as you can understand that this missingness can happen for many different reasons. So say for example, even for this income variable, there are many variables that are predictive of income, not only this education and the socio-demographic status, but many other variables. But it can happen that you may not have all of those information in your dataset. So to make the imputation values more plausible, what you would want to do is to incorporate as much as predictor as possible to try to impute a realistic value of the missing value. But again, we have to be a bit careful, because if there is a overfitting problem, that would create a issue, because essentially these imputation models we are talking about, some of them are predictive models, and obviously, as we have learned earlier, that in prediction, if we are overfitting, that will also create a problem. If we have some unmeasured variables that are predictive of what we are trying to predict, that will also create some problem. So we will have to think a bit more carefully about how to build that kind of imputation model. That part I will talk a bit later. Alright, so the third type of problem is missing not at random, or MNAR, or sometimes we call them NMAR. So in this scenario, when we see a variable's values being missing, under this assumption, we generally do not know what is causing this, and at least from the point of view of the dataset that we have in our hand, we cannot explain this, and we assume that the missingness may be explained by some unobserved variables that are not captured in the dataset. And in this scenario, again, the missing values and the observed values have some difference, but we don't know how they're really different. So in this scenario, even if we include a large number of predictors in our imputation model, it might not help. We might still have some residual problems in our prediction of the missing values. So we have to be very careful about these type of situations. So how do you really test? So there are some formal tests of identifying the problems of missingness, but there are no easy ways to just say that yes, this is a problem versus no, this is not a problem. So this requires a lot of subject area understanding why a variable's value can be missing. Say for example, for the income example, one can try to explain why those income values were missing for certain people but not for the other people. And as an analyst, you need to have a very good understanding of how the data was collected, the data collection process, and how the data was gathered and all that. There are some diagnostic tests available, and in the lab we will see some of those. But we have to understand that when we see some difference in the missingness for the observed values versus the missing values, distinguishing between the MAR and MNAR using just the empirical or the observed data is very hard, and there is no way to guarantee that this problem is under the assumption of MAR or this problem is under the assumption of MNAR. So we have to be very careful about how we interpret our results. In general, we always try to justify why we are doing a missing data type of analysis, and usually people try to justify that their missing data analysis is justified because their data is under MAR assumption, where some of the other predictors can help impute those missing values in a reasonable way, but guaranteeing that after this missing data problem, after this missing data analysis, the problem will go away is not really feasible in most scenarios. Alright, so in here we are going to talk about how to address the missing data problem. So there are some correct ways, and obviously there are some ad hoc ways that are not really the correct ways, and we are going to talk about them in this particular section. So in this section, let me talk about some of the approaches that people generally use. The first approach is not think about missing data problem at all and blindly go with whatever software result is giving you. So you just run a regression model and you don't really know or don't really care about what the software did to come up with that result. Did it somehow address missing data problem somehow, or did it just delete all of the incomplete rows? And to be honest, many people do that, and for a methodologist this can be frustrating, but there is no way around it unless people learn more about missing data approaches. The one very common approach to fill the data is just to use the mean. Say for example, if you are missing the age category, you can simply impute the mean of age, and there are some logic for it. They say that if I'm inputting just the mean, I'm not necessarily changing any pattern in the data set, but essentially keeping the power same. Again, I mean, just replacing all of the values by mean might not be the best approach in most scenarios. One other approach people do is they use the missing category indicator, and they just add a category that income level this, income level that, less than 20,000, between 20 to 50,000, above 50,000, and then there is a missing categories. Usually for the categorical variables, they do this, and this gives them a false sense of security that I'm doing something, I'm not omitting the problem or imputing the mean values, right? And they also get a coefficient when they run a regression associated with that missing category. But this is not really a good solution for most realistic problems. One other approach that is very popular in terms of the longitudinal data analysis is that whatever value that was measured, just impute that value. So for example, if your income is missing in 2020, just impute the value that was in 2019, and that might not be the best value, but this is the most recent value that we have. Even with that approach, it has been shown that this might not be the best approach even in a longitudinal scenario. And of course, when people do not do anything about missing data problem, they simply try to do a complete case analysis. But unless you can justify somehow that your data is, whatever value that are missing is following the missing completely at random assumption, your complete case analysis is not really valid. Alright, so in terms of the principled approaches, there are two type of approach. One is the single imputation, one is the multiple imputation. And the general rule of thumb is that if you have a variable that has more than 5% of missing, then you should impute. Or if you have a data set where you have 5% of missing overall when you combine all of the missing values from all of the variables. If that is only less than 5% of the missing, then you do not need to adjust for the missing data problem. But again, I mean, this is just a cut point that we are talking about, and whether this is universal, applies to everywhere, all data problem, I don't think so. But depending on your data, you might have to judge for yourself based on your subject area knowledge whether this is something that is negligible, less than 5% or not. Alright, so in terms of single imputation, the basic idea is that we would impute the missing values. Say for example, if you have age variable and if you have a person who has that age variable missing, there are a couple of things that we can try to do. We can try to pick a age value from a different person at random, and we can then try to impute that age value, say for example age 34, to the person who did not fill out the age box in their form. Or the other criteria could be that we try to match on key variables. Say for example their income category, their cholesterol level, maybe their BMI, whether they are married or not. So we match on couple of key variables, and then we have a pool of subjects who fit into that particular category of key variables, right? So everybody's whose income is more than 50,000 to 80,000, their BMI level is say around 29, and whether they are college educated or not, whether they are married or not, based on all of these, we have a pool of people in our data set, and then from those pool of people we try to select one person, and then we simply take that person's age and impute it to the person who did not fill out the age. So this type of approach is known as hot deck imputation, when we are trying to impute based on matching from the same data set. But if we do the same from an external data, then we call that cold deck imputation. Alright, so there are more generalized method of single imputation than this hot deck and cold deck. We can simply impute the mean as we have described earlier, or we can try to use regression to predict the missing value. Say for example, y is age, and that's the predictor variable could be educational status, married, BMI, cholesterol level, and things like that. And based on that, we can try to predict what would be the predicted age for that person. So this is kind of a deterministic model where we have just the intercept and slope and predictors. So if you run this regression again, you will again get the same predicted age for that person. But one of the key problem with this single imputation is that we are not really getting any variability in the result, and we are imputing the value as if that value was observed. So there should be some uncertainty when you are imputing some value, because I do not know whether that is the exact value. But when I'm doing single imputation, I am doing it like that. I'm treating it as the exact value. So there is this stochastic regression imputation where we do the regression as usual, but we add some error terms. So every time we do this regression, we will get a slightly different y hat. Sometimes it could be 32 age, sometimes it could be 31. So that gives you some sense of variability that is accounted precisely because that value is that we are imputing is not observed. And the last method is known as predictive mean matching, that I'm going to explain in the lab a bit more. But in general, this is a type of hot deck method, but that uses the combination of the regression method. And these predictive mean matching or PMM methods are very popular because of their very nice statistical properties. One of the reasons this method is popular is because it imputes a real value instead of a averaged out value, and that gives some protection against extrapolation. Again, I'm going to talk about this in the lab in more details. As I have explained a bit earlier, one of the problem of this single imputation method is that there are no variation. So whatever value we are imputing, those are just the fixed value. So even for the stochastic regression method, if you are fixing the error term when you are determining the predicted values, that gives you some hope of some additional variability that should be in a imputed data, but even that might not be adequate for us to give a proper standard error, and the uncertainty is in the missing data is not represented well even in that stochastic regression approach. So what is this multiple imputation, and how can this multiple imputation capture the uncertainty in the missingness? So let us discuss the steps of multiple imputation, and then it might be a bit more clear. So the first step is to figure out the imputation model, that means the prediction model that would give you some idea of what values are reasonable for imputing the missing value. Say for example, if age is missing, then you would want to gather all of the variables that are predictive of age. It does not matter whether they are highly predictive or slightly less predictive. What matters is that if they are predictive of age that is missing for some subjects in your dataset, we will try to incorporate those in our imputation model. Of course, there are some additional considerations of overfitting and all that, but to be realistic about our MAR assumption, we usually try to build models that incorporates any correlated information about the missing value. And of course, when we try to feed this model, we feed this model in the observed data, and then we are essentially sampling from the predictive distribution of the fitted model. So we are not really getting any exact value, but we are mainly interested about the predictive distribution that we are getting from the fit, and then from that predictive distribution we are imputing the missing values, and that's where we are inducing some variability, so that every time we are doing this missing data imputation, we are essentially imputing some different copies of the predictive distribution So that's how we are not being boxed in a simple imputation type of scenario where every time we do imputation we essentially impute the same stuff. And once we do this, once we are done with our imputation model and the model fit, then we go to the second stage where we essentially create some copy of the dataset. Ideally, people use either 5 copies of the dataset or 20 copies of the dataset, but if your computing resource allows, you can go even more, and in the diagnostic setting section of our lab we will show why that matters. And then in each of these datasets, say for example for our case, let's assume that we are going to go with 5 copies of the dataset, and each of these 5 dataset we are going to impute the missing values from the predictive distribution from the fitted model. So this is not just one value, so this is a distribution, and then from that distribution we are going to impute those sampled values in our to replace our missing values. And since we are imputing all of these values, we are essentially generating a dataset that is complete, but each of these datasets are slightly different in the context of all of those missing values. Say for example in one copy, for one person who has a missing age, I can impute an age of 34, and then for another dataset from that predictive distribution I can impute another data of 36. For another person it could be 34 again, and for another person it can be 37, and all that, and that variation will be necessary for us because that is allowing some uncertainty because of the missingness. Alright, so now we have 5 copies of entire dataset, and then we say for example we are interested about regression, right? And in the regression, say for example cholesterol level is the outcome, age is a covariate, income is a covariate, right? And since we have our datasets that are complete, so essentially what we are doing now is that in the 5 different complete datasets we are going to fit our 5 regressions, right? And those 5 regressions results will not be exactly identical because the datasets are slightly different now. And then we will get the models or model coefficients from all of these 5 different models, and then we will get 5 different copy of the beta coefficient or the slope for the age variable, say for example. And then using the Rubin's rule, say for example for averaging out these values, Rubin's rules are used to combine the values and calculate the standard error using certain formulas. So those formulas are then used to combine and get a single estimate of the odds ratio, say for example, and the standard error of the odds ratio. So eventually we are getting single estimate, but to get into this single estimate we are going through all of these steps, and these are the basic steps of doing multiple imputation. So the step goes like this, and you can check out the book by Thomas Lumley, and in chapter 9 he describes about this, that if you have a incomplete data, think about, say for example here I'm thinking about 3 different copies. Previously I was talking about 5 copies, right? So in this picture I'm just talking about 3 different copies of the dataset where I am imputing the missing values based on the imputation model that I build, right? And after imputing, all of these imputed data will be complete data. So the original data, if there was 1000 participants, here there will be 1000 participant here, 1000 here, 1000, because I'm not deleting anyone. I'm just imputing the observations that are missing, and from this data I will get a beta coefficient of the treatment effect or the exposure variable, and I will get another treatment effect here, I will get another treatment effect here, right? And then I will pool or aggregate all of these three different results of the odds ratio or the beta coefficients, and then I will pool them into one value. But in the process, what will happen is that I will also pool the results to get the reasonable version of the standard error. What is the reasonable version of the standard error? It is basically a standard error that take into account of the fact that some values were missing, and we imputed some values based on the predictive distribution of the imputation model that we have built, but there is no guarantee that the value that we have imputed is the true value. Say for example, for one age, if we impute just a value of 34, does that how are you making it different than all of the other values about which there are no uncertainty? If someone reported their age as 35, that is their age. If someone reported their height as some 5 foot 3 inches, and then that is their height. But if a value is missing, then there is some uncertainty about the imputation value that you are imputing. And using this multiple imputation process, we are basically taking into account of that uncertainty. All right. So obviously this is a multi-step process and the analysis can be complicated, but at least the uncertainty is taken into account. That was the major problem associated with the single imputation. It is worth talking about what should be the predictor for your multiple imputation. So any variable that is predictive of the missing value, say for example the age, if that variable has some missing values, then any other variable that are predictive of that age variable should be in your predictive model. If there are some values that are predictive of age, say for example height could be one variable that could be predictive of age, but you might not have that variable in your data set. So in that case, what will happen is that obviously that relationship between height and age cannot be utilized to get a better prediction of age. So also one other interesting fact about missing data imputation model is that when you are doing an analysis, say for example cholesterol is your primary outcome of interest, and say for example BMI is your exposure of interest, and age is a covariate, but you have some age of some subjects that are missing, right? So in this case, in your imputation model, age is the outcome model. So there are two models we're talking about. One is the regression model, that is the ultimate analysis model that you are thinking about, but in that process there are some missing values in age, so you need to impute those age values. So in the process of imputing those age values, age is the outcome of your imputation model, and in that imputation model even your outcome is useful, because say for example age can be related with cholesterol, here cholesterol being the outcome of your main analysis, and that outcome variable can give you some information about your age. So it is even though we have this level of outcome for the main analysis, for the purposes of your imputation model, that outcome can be a predictor. And generally, it is encouraged that we use those outcomes in our imputation model. Also, subject area knowledge is very useful to build imputation model. From the subject area knowledge, we can try to figure out why the variable was missing, and then we can also think about what are the variables that are predictive of the missing variable, or what are the reasons of the variable being missing, what are the variables that are highly associated with the missing variable, and all of those could help us try to build a better prediction model. Alright, so in terms of the imputation model, one other type of predictors are known as auxiliary variables. So these auxiliary variables are those variables that are not really useful for your main analysis. Say for example, the cholesterol versus the BMI. In that relationship, say for example, where you live or how much is your income might not be relevant, but when you are imputing your age variable, for that age imputation, external variables that are not really considered for the main analysis can also be useful. And even though hypothetically we can think of the overfitting problems and things like that, but research has shown that adding those additional variables might not do too much harm in your imputation process. Also, when you are adding more and more variables, you are only making your MAR assumption more plausible and stronger. So in the survey data analysis context, even say for example the strata and cluster variables can give you some geographical locations of the subjects, and that could be maybe useful for including in your imputation model as well. Alright, also your predictors in the imputation model can be rich in terms of model specification. What that means is that you can also try to think of higher order terms. And if you have a reason to believe that the missingness in the exposure group and the unexposure groups are following different patterns, maybe it can make more sense to model them separately. For the exposed group, model them separately. For the unexposed group, model them separately. If you think from your subject area expertise that that is the best way to go. Alright, one common problem even with multiple imputation is that people rarely check the diagnostics and convergence of the multiple imputation. Many of the researchers simply use the multiple imputation and do not really check the convergence or diagnostics, and even though this is not easy, and most of the diagnostics are based on visual inspections, some are based on some tests, but it is always a good idea to draw the diagnostics and convergence plots to get a good sense of how good was your missing data compared to the observed data that you have. In the sample survey, we learned about one interesting idea of design effect that compares the estimates variance under a complex survey divided by the variance from a simple random sampling. And here in the missing data literature, we have a similar statistic. It's known as the percent missing. It basically compares the precision of an estimate when you have missing data versus the precision of the estimate when there was no loss of sample size because of missingness or non-response. And usually in the statistical softwares they report this percent missing. and this gives you some idea about how much precision you are losing because of the missingness. So in terms of the variable selection, this multiple imputation approach can be helpful, and there are 3 different ways we can do variable selection under the missing data scenario. The first one is, say for example, when you have a very large M, that means the number of imputed data set. So if you have 100 imputed data set, and in those 100 data set you run a stepwise regression, say for example, and then try to see in how many of these imputed data set one particular variable, say age, was selected. And then if you find some of the variables were selected more than 50% of the times, then you make a subset of them, and then one of the interpretation of that could be that those variables that are selected 50% of the times are useful variables, and that is the majority approach. And note that Bootstrap has a very similar approach of variable selection, but Bootstrap and this MI process or multiple imputation process are not exactly the same, and they might give you different results as well. Stack is a process where, say for example, if you have 100 dataset, you combine all of the 100 dataset to one dataset, and then you do variable selection in that one dataset with very large number of observation, and then whatever variables that you can come up with that one regression will be the final solution from that stack solution. The final approach is the world test based approach, where you can fit 100 different models, and you can also compare nested models. That means, say for example, for age variable, once you add age variable and once you do not add age variable, and then you compare these 100 different models with one another, and you can essentially do a generalized world type of test utilizing the ideas of these Rubin's pooling ideas or the estimates, and that is an approach that is known to be better approach compared to the majority and stack rule, and all of these approaches I will explain in the lab. One common problem is your outcome variable itself may have a lot of missing values, and then simply deleting them does not feel right, but imputing them does not feel right either, because if you are imputing your outcome variable, you are essentially manipulating your outcome somehow. So one approach that people use is known as the do the multiple imputation including the outcome variables, but then delete the outcome the observations that are associated with missing outcome information, and we do that because we want to get the strength of the outcome as well, and with a larger data set to build a more stable and good imputation model. And that's where even the observations with missing outcomes can help, but eventually when you do your analysis after the imputation, then do not use those observations where your outcome was imputed. And obviously this is not a foolproof approach, and there are some back and forth in the literature about whether this is a good approach or not, but this is one approach that is popularly used, and this is known as MID, or missing imputation then deletion. All right, so what about the survey data? I mean, we all learned about this multi-step multiple imputation process, but can we use survey data analysis to deal with some of the missing data problem? And the answer to this is that even though this is a multi-step process, but the process is exactly the same when we are dealing with the missing data in the surveys. We can essentially extend the multiple imputation approach to the survey data analysis, and in the lab as well we will see something, some examples that will be helpful for you to understand how to do that. All right, so in the paper that I have shown at the beginning of the slide, that discusses some of the common problems in the literature, and some of these we have already discussed, that some of the approaches people use are suboptimal. Sometimes they do not even report the missing percentages properly. They do not really discuss about what type of missingness that is going on. They just do a imputation maybe, but often do not explain why it is justified to do a imputation in their dataset. Also, often they say that we have done some imputation, but they do not mention that it is whether this is single imputation or multiple imputation. And as I said, justifying your assumption is very important, because either single imputation or multiple imputation, both are done under the assumption of MAR, or missing at random. If missing at random is not justifiable, then we cannot do this single and multiple imputation and claim that our results are perfect. Also, when we are analyzing a data using the missing data analysis, we always should report what is our imputation model, what were the predictors, whether there were any auxiliary variables or interaction variables used or not, how many imputed data sets were used. Those are the things we should report. We should also report which software we are using, which software version we are using, because different softwares use missing data defaults differently, so it is a very good idea to report the software and version. So if you are interested more about missing data analysis, there are some additional resources that talks about the longitudinal analysis, and there's some interesting tutorial of multiple imputation that you can refer to. Thank you.